Hi, everyone, and welcome to Chapter 13 on repeated measures and multifactorial ANOVAs. Previously, we discussed the one-factor ANOVA. While one-factor ANOVAs are beneficial, studies are often more complex than that. First, we are going to talk about repeated measures ANOVAs, where several treatment conditions can be compared using a repeated measures design. Just like a repeated measures t-test, in a repeated measures ANOVA, the same participants participate in every treatment condition. Say we ask the question, how do different activities affect stress levels? And we want to compare three methods: journaling, mindfulness meditation, and physical activity. Previously, we would have a group of participants and assign each person to take part in one of these activities, and then we would compare the groups. But in a repeated measures design, everyone experiences every treatment. So maybe all participants complete a journaling exercise for a week, and then they complete a stress questionnaire. And then everyone switches over to mindfulness meditation for a week and completes that same stress questionnaire. And then again, everyone switches over to physical activity for a week and completes that stress questionnaire. So instead of comparing different groups, we are comparing people to themselves in different conditions. In a repeated measures ANOVA, we have the same hypotheses as before, and we are still finding an F ratio. But there is a difference in terms of the conceptualization. If you remember, in a one-factor ANOVA, the F ratio consists of treatment effects plus differences due to chance in the numerator, divided by differences due to chance in the denominator. But previously, chance included individual differences, people just naturally being different from one another. But now we are using the same individuals in each group, which allows us to control for that error. This means that chance is only due to random error now. And between this difference and the fact that we are measuring people multiple times, this changes our analyses. There are three new notations to know. Capital N is the total number of scores, not just the participants. P is the sum of each participant's score, and N is the number of subjects in each group or condition. And just as a reminder, K is the number of treatment conditions, and GM is the grand mean. Here's the equation table for the repeated measures ANOVA. Feel free to pause to write these down, print, or screenshot for later. We'll have an example working through each of these. But what I want to draw your attention to now is the way the table is set up. We have between and within treatments like before, but now the within treatment variance is further divided into two pieces. Between subjects variance, so variance due to differences between people in your sample, and then error variance, which is due to random chance. With this, let's go into an example. Say a psychologist is interested in whether different medications improve short-term memory performance. To test this, the researcher measures a group of participants under 4 different conditions: a placebo, drug A, drug B, and drug C. Under each condition, the participants must recall items on a memory test, where higher scores indicate better memory performance. Examining the data below, is there a difference between drug type and memory? So just like before, let's set up our hypotheses. The null hypothesis is that each of the groups will be equal to one another. Our null hypothesis is that at least one group is different. We'll set our alpha to 0.05, and then we need to find our critical value. To find the critical value using the F table, we need degrees of freedom between treatments and degrees of freedom error. Let's start with finding degrees of freedom between treatments. This is K minus 1. We have 4 groups, so 4 minus 1 is 3. And then there's a little bit of a process to finding degrees of freedom error. We'll start with finding degrees of freedom within treatments, which is N minus K. We have 20 total data points, so 20 minus 4 is 16. And then we find degrees of freedom between subjects. This is N minus 1. We have 5 participants, so 5 minus 1 is 4. And then we can find degrees of freedom error by subtracting degrees of freedom within and degrees of freedom between subjects. 16 minus 4 is 12. So again, using that same F table, F312 gives us a critical value of 3.49. Before we go any further, let's plug those degrees of freedom into our table before we forget. Here are the numbers we just calculated, and that leaves us with just needing degrees of freedom total in this column. Degrees of freedom total is n minus 1. So again, we have 20 data points because we have 5 people taking part in 4 conditions. 20 minus 1 is 19. And now we can move on to finding the sum of squares. The equation for the sum of squares between treatments is the sum of n, which is the number of participants, times the mean for each group, minus the grand mean squared. So let's bring up that data set and find the mean for each condition. We add the total number of scores and divide by the number of scores available, and that gives us 1 for placebo, 2 for drug A, 4 for drug B, and 5 for drug C. And then we can find the grand mean by adding all of the scores and dividing by the number of scores available. This gives us 60 divided by 20, which is 3. And now we can do that calculation. I find that making another table is helpful for organization, but it's not required. In the left column, we have the means of each group, and then on the right, we can plug these numbers into the sum of squares between treatment formula. So for placebo, we have 5, which is our number of participants, times 1, which is the mean, minus 3, the grand mean, squared, and that gives us 20. We do this for each group and then sum the scores, which gives us 50. So our sum of squares for between treatments is 50. For sum of squares within treatment, we use the equation the sum of x minus the mean squared. So we sum the sum of squares for each group. And at this point, you should be pretty familiar with the sum of squares table. We'll bring up the means calculated on the last slide, subtract the mean from each score, square it, and then total the score. So this gives us 8, 8, 6, and 10. We sum these numbers, and that gives us 32. So our sum of squares within treatment is 32. Our sum of squares between subjects is a new calculation. We have p squared divided by k minus the sum of x squared divided by n. Again, p is a total score for each participant. So looking across the table, we add the scores in each column, which gives us 20, 12, 12, 8, and 8. And then we square each of those numbers, which gives us the numbers shown here. But we don't sum them yet. Remember that the first part of the equation is p squared divided by k. So we have to divide each number by the number of groups. This gives us 400 divided by 4 plus 144 divided by 4, and so on, which totals to 204. And that is the first part of our equation. The second part is the sum of x squared divided by n. Remember that we already totaled all of the numbers when we found the grand mean, and that was 60. So 60 squared divided by 20 is 180. And now we can subtract these. 204 minus 180 is 24. So our sum of squares between subjects is 24. Let's fill the table with the 3 sum of squares we just solved for. This leaves us needing the sum of squares error and the sum of squares total. We find the sum of squares error by subtracting the sum of squares between subjects from the sum of squares within treatments. So 32 minus 24 is 8. Sum of squares total is calculated by adding the sum of squares between treatments and the sum of squares within treatments. So 50 plus 32 is 82. And now we can find the mean squared. Mean squared is calculated similarly for each source of variance. You take the sum of squares and divide it by the degrees of freedom for each category. So for mean squared between treatments, we have sum of squares between treatment divided by degrees of freedom between treatments. So 50 divided by 3 is about 16.667. We do the same thing for within treatments, and that gives us 32 divided by 16, which is 2. We do it for between subjects. 24 divided by 4 is 6. And then we do it one more time for error, where 8 divided by 12 is about 0.667. And finally, we can solve for f, which is mean squared between treatments divided by mean squared error. So 16.667 divided by 0.667 is about 24.988. And this is larger than our critical value of 3.49. So we reject the null, at least one group differs. And now we run our post hoc test to see which groups differ from one another. The Tukey post hoc test is very similar to the one we used previously. The difference is that we use mean squared error instead of mean squared within. Other than that, the process is exactly the same. We use the standardized range table as we did before to find our critical value. Please see the previous lecture if you need a refresher on this process. But using that table, our critical value is 4.2. And then we compare two groups at a time and make sure that each group is being compared. Because we have 4 groups here, there are 6 comparisons. Placebo versus drug A, B, and C, and then each drug being compared to one another. So again, 6 total analyses. I'll do 2 of these as an example, but I don't have time to go through all of them in this lecture. For placebo versus drug A, you can pull up the equation and plug in the numbers. The mean for placebo is 1, and the mean for drug A is 2. And then we divide by the square root of mean squared error, which is 0.667, over n, which again is 5. This gives us negative 2.74. We take the absolute value of that, and we see that this is less than the critical value, so there is no difference between groups. We do the same for placebo versus drug B, plugging in the means and keeping the denominator the same. And this is 8.219, which is greater than our critical value. So there is a difference here between groups. And then from here, you can continue with the comparisons. Here's the result of the comparisons in case you want to work through each one. The means are provided so you can see whether or not there was an increase or decrease in scores. And lastly, we need to find the effect size. We use eta squared again, and we calculate this by dividing the sum of squares between treatments by the sum of squares between treatments plus sum of squares error. So using these numbers from our source table, this gives us 50 divided by 50 plus 8, which equals 0.862. And we interpret this the same way. This number shows that 86.2% of the variance is accounted for by the treatment effect. Here's a practice problem for you to try on your own. A professor wants to test whether different study methods affect exam performance. The same 6 students use all 3 study methods before taking a quiz. Using a repeated measures ANOVA with p equals 0.05, is there a difference between groups? If so, run a post hoc and find eta squared. Pause to solve. The answer will be shown in 5 seconds. Here are the answers to that question. Just like before, use the slide to check your answers and then go back to earlier parts of the lecture in case you need help. From here, we are going to switch gears a little bit. Like we talked about at the beginning of the lecture, one-factor ANOVAs are great, but tend to be simpler than real-life studies. Most studies running an ANOVA use a multifactorial design, meaning that there is more than one factor. You'll learn more about multifactorial designs if you take research methods, but for now, we'll talk about two-factor ANOVAs, where the influence of two factors can be evaluated. If you remember from last lecture, we asked the question, does therapy reduce symptoms of anxiety in college students? That question had one factor, right? Therapy. And then there were three levels within that factor, consisting of three different types of therapy. But we know that therapy isn't the only factor relating to anxiety. Medication can also help, and the people in our study might already be using anxiety medication. So maybe we make this a two-factor design, looking at both therapy and medication's effect on anxiety. And we look at whether individuals are taking no medication, a low dose, or a high dose. By adding the second independent variable, we now have two factors with three levels each. You won't have to run analyses on this, but you should be able to conceptualize the idea. Here is another example for us to dive deeper into. Heat has been shown to increase aggression. The color a team wears has also been shown to increase aggression, where dark clothing equals more aggressive behavior. We can look at these variables individually, as well as look at it when it is hot and they are wearing dark clothing. So to help conceptualize this, it can be helpful to make a table. On the left, we have light uniforms versus dark uniforms. And on top, we have temperature, not hot and hot. And then within the boxes, we have overlap with uniform color and temperature. So wearing a light uniform and having it be not hot or hot outside, and wearing a dark uniform and having it be not hot or hot outside. If we were to run this study and examine behaviors of each of these four groups, we would examine this data in two ways. We would look at main effects and interactions. Main effects are the mean differences among the levels of one factor. Think the main groups that make up the left column and top row of this table. Here we could look at the main effect of uniform to see if just wearing a dark uniform increases aggressive behaviors. This means we also have a main effect of temperature. We can see if just hot weather affects aggressive behavior. But we also have interaction effects, which refer to when the effect of one factor depends on the levels of a second factor. This is that middle area of the graph looking at both color and temperature. By examining this interaction, this would allow us to answer the question of whether uniform color and temperature together affect aggression more than either variable alone. It helps us to paint a bigger picture of what is going on and why people behave the way they do. If we were to analyze this, we would have the number of aggressive behaviors for those in each group, and then we would examine the change in means across the groups. When we look at the main effect of uniform colors, we see that there is a greater number of aggressive behaviors when players are wearing dark colors. Of course, we don't know if this increase is statistically significant, but in this example, we'll pretend that it is. Then we can look at the main effect of temperature. Again, there's a significant increase in aggressive behavior when it is hot. So there are two main effects in this example. Then we can look at the interaction between the variables. When athletes are wearing light uniforms and it is hot, there's a 40-point increase in aggressive behavior compared to when it is not hot. But when players are wearing dark uniforms, there is a 60-point increase in aggressive behavior, showing that uniform color and temperature combined increases aggressive behavior more than either variable alone. Because there are two potential main effects and one interaction effect, there are three F values provided in a two-factor ANOVA, and the significance of each depends on the p-value. So you might have no significant main effects, but a significant interaction. So if you ever ask a question, especially in a psychology class, and get the answer, it depends, it's likely due to an interaction among variables. Again, this helps us to better understand the nuance of behaviors. Lastly, it can be helpful to graph factorial ANOVAs to better understand the results. For instance, this graph on the left compares actors and comedians from both the US and France on some variable of interest. Say this is the amount of money earned. Actors show higher numbers than comedians on this variable, but the numbers are the same regardless of country. So we would say that there is a main effect of occupation such that actors earn more money than comedians. But the story changes if the graph were to look something like this. If we were to draw a line from each bar, it would cross, showing an interaction between occupation and country, such that US actors have greater pay than French actors, but French comedians have greater pay than US comedians. And that is all I have for you. If you have any questions, please let me know.